Hi everyone, it's Mrs. Hanson. I'm just recording a quick video to clarify some points from our Chapter 5, Lesson 2, specifically related to empirical and molecular formulas. This comes out of Section 5, out of Chapter 5, and I know it will be your topic of lab very soon as well. So just to define the two terms, an empirical formula, as you can see, is the simplest whole number ratio of atoms in a chemical formula, whereas a molecular formula is the true formula for how we actually find that molecule in nature. And I have an example here where I can show H2O2, which is a common name for what we refer to as hydrogen peroxide. So again, this is one that you are going to run across with a common name. It is not called dihydrogen dioxide, but rather just simply hydrogen peroxide. You probably have this in your medicine cabinet at home. You put it on an injury and it starts to bubble oxygen and kind of clear out any bacteria and so forth. H2O2 is an example of a molecular compound that we find in nature connecting two oxygens and two hydrogens in this particular bonding order. So this is what we refer to as its molecular formula, its true formula, the way we find it in nature. Notice, however, that 2-to-2 subscript ratio can be reduced to a simpler, low whole number ratio of those atoms. Reducing that 2-to-2 ratio gives me an empirical formula for that compound, HO. As another example, we have in nature simple sugars, C6H12O6. It's a molecular formula for a molecule known as glucose. Any monosaccharide shares this particular molecular formula where we see 6 carbons bonded to 12 hydrogens bonded to 6 oxygens. That's its true molecular formula, the way we find it in nature, the way we find it in our body. However, notice that this ratio, 6-12-6, can be simplified. It can be reduced to a whole number ratio by dividing it all through. We have a CH2O empirical formula. The 6-12-6 can be cut right in half to a 1-to-1. So that would be the empirical formula, the lowest whole number ratio for the molecule glucose. I wanted to kind of share where you would apply this in your ALEX. So for instance, I just took some screenshots of problems that you're working in your ALEX assignment, Chapter 5, Lesson 2. And I just picked question 7, but I think question 9 is also very similar. So it looks a little scary, but once we talk through it, you'll find that it's not very scary at all. We just have to understand what it's really asking. So here we have these molecular formulas that are given to us in kind of these bond line formulas. Notice that it's just showing us connectivity of atoms. What I want to do with the picture is just count how many of each atom I have. So notice here I have 2 carbons, I have 2 hydrogens, and I have a single oxygen. So what I've just done is rewritten, instead of in a bond line connectivity formula, I'm just simplifying it to show how many of each kind of element there are, C2H2O. I'm going to do the same strategy for molecule B. Let's count how many carbons there are. 1, 2, 3, 4, 5, 6. So I have C6. Let's move to the hydrogens next. 1, 2, 3, 4, 5, 6. And let's count how many oxygens. 1, 2, 3, 4, 5, 6. I'm just going to re-record that one so we can create kind of a column of compound A through D going down. Let's do the next one, starting with your carbons. 1, 2, 3, 4. There's 4 carbons there. Let's do hydrogens. 1, 2, 3, 4. H4. And let's count oxygens. 1, 2, 3, 4. And one more to go. Starting with carbons. 1, 2, 3, 4. And hydrogens next. 1, 2, 3, 4, 5, 6, 7, 8. And oxygens last. We have 1, 2 of them. So here I've written out what we're going to call the molecular formulas for each of those individual molecules that were drawn for us, showing connectivity, bond line structures or Lewis dot structures, heading our way next chapter. What we want to do, and we're told to do, is to find the empirical formula for each, and then see if you notice any that are identical and group those together. So here in my first compound, I have a 2 to 2, and it's not there, but I know it is. I have a 2 to 2 to 1 ratio. 2 to 1 is already in its lowest whole number ratio. It cannot be reduced. It cannot be simplified any further. So with this particular molecule, the molecular compound is identical to its empirical compound. Let's go to the next one. I have a 6, 6, and a 6 subscript ratio. That certainly can be simplified since they're all the same number. The simplest ratio would be all ones. Divide through by 6s and you get a 1 to 1 to 1 subscript ratio. The empirical formula represents that 6 to 6 to 6 being reduced to the lowest whole number form, 1 to 1 to 1. And you know what else? I see this doing the same thing. This 4, 4, 4 in compound C, it can also be rewritten as CHO, the lowest whole number ratio, all divisible by 4, making them ones in the lowest form possible. One more to examine, and that is compound D, with the ratio 4, 8, 2. So this one can be reduced by dividing through your subscripts all by 2, 4 divided by 2, 8 divided by 2, and 2 divided by 2. I get a C2H4O. After we've reduced them, we're just trying to find patterns. Do you notice any that reduce to the same empirical formula and group them together? So I notice that compound B and C are identical when reduced to the lowest form, so I can group those together. I'm going to just call that group 1. The first compound, compound A, is unique. There's no other compound with a 2 to 2 to 1 subscript ratio. I'm going to call that group 2, leaving this one as group 3. Now, friends, it does not matter what you call group 1 or what I call group 1. It just matters that you've grouped the same empirical formulas into the same group. So if you called this group 1 and this group 2 and this group 3, you would get 100%. They're grouped properly. If you had called this group 1 and this group 2 and this group 3, you would be given 100% credit because I've grouped in the same category the molecules that shared the same empirical formula. So please know that there is more than one right answer. The only way that you'll get marked wrong is if you didn't include all members of a group that shared the same the same empirical formula. So let's talk through that strategy one more time, one more example, just to kind of clarify. Try another. Same Alex homework, but I'm just trying another. Step 1, let's count how many of each atom we have. I see 2 carbons, 1, 2, 3, 4 hydrogens, and 1 oxygen. So there is my representation of a molecular formula coming from that bond line formula. There's 2 carbons, 4 hydrogens, and 1 oxygen. C's, H's, and O's. Let's count in compound 2. 1, 2, 3, 4 carbons, And let's do H's next. 1, 2, 3, 4, 5, 6, 7, 8. And how many oxygens? I see 1, 2, 3, 4. On to compound C. 1, 2, 3, 4 carbons. Let's do H's next. 1, 2, 3, 4, 5, 6, 7, 8. And the last one, oxygen. 1, 2, 3, 4. Alrighty. And last but not least, we have the compound D. 1, 2, 3, 4 carbons. We have 1, 2, 3, 4 hydrogens. And how many O's? 1, 2, 3, 4. All right, so here are those molecular formulas, which is just counting how many of each atom we have in a simplified form. So taking away the bonds that show connectivity and putting it rather into just simple ratios here of showing how many of each atom, how many of each element we have. So let's move from the molecular to the empirical formula, which means, can we reduce the ratios at all? So in my first example, a 2 to 4 to 1 ratio is already written in the simplest form. There's nothing that I can divide through a 2, 4, 1. As soon as you notice one of your subscripts is a 1, I can't divide it down into a simpler whole number. So this one, a 2 to 4 to 1 subscript ratio remains. The molecular formula is the same as its empirical formula. In our next compound, a 4-8-4 subscript ratio can be reduced to a simpler form. We'll divide through all of them by 4, giving us C1, H2O. 4-8-4 cut in half, cut down to the simplest form, we have a 1-to-1 ratio. And I can do the same thing for the next molecule. Because those are identical subscript ratios, a 4-8-4 is reduced to its simplest form, a 1-to-1. And finally, in this last compound, they're all the same number, so they can be reduced down all to the subscripts of 1, CHO, the simplest whole number subscript ratio. Now we just simply examined, do you see any that are alike? And again, this problem just coincidentally worked out that compound B and C are identical. So it doesn't matter what group number I call them. It can be group 1, 2, 3, or 4. I just have to make sure I'm categorizing them as the same group. Sorry, I put my elbow on the plus sign. So we'll put that back. I'm just going to call this group 1. We have 3 unique groups. So I'm going to just call them group 1, 2, and 3. But again, let me emphasize, as long as you're grouping the same compounds that share the same empirical formula by putting the same number, you can give them whatever number you want. We just need to show that of the 4 compounds, 2 of them share the same molecular to empirical formula subscript ratio and therefore have to be assigned the same number. And you can see that that's the same strategy over and over for several of these particular ALEX questions on covalent bonding. Come up with the empirical formula, reduce them to the lowest subscript ratio, and then just categorize, do any of them have the same ratio? Make sure you put those into the same group. There is another problem I just grabbed a screenshot of. What are the molecular formulas and empirical formulas of this compound? So remember, the molecular formula is just the true formula. Let's count how many of each atom we have. 1, 2, 3, 4 carbons. There are, let's count H's next. 1, 2, 3, 4, 5, 6, 7, 8. And then how many oxygens? I see 2 of them. So the true molecular formula, C4H8O2. can that be reduced to a simpler ratio? And the answer is yes. I can divide through all those subscripts by 2, and when I do that, 4 becomes a 2, 8 becomes a 4, and the 2 turns into the 1. So you would type in C2H4O for the empirical formula, that lowest ratio possible. And one last note, as you're working through ALEKS, I've noticed that when we are asked to name the covalently bonded compounds, once in a while you'll run into a common name. So I'm going to just let you know that you should know these. Ammonia is a common name given for the molecule NH3. It's a common household ingredient, probably in your kitchen, used as a cleaning agent. Ammonia, NH3. We learned in the polyatomic ion chart about ammonium. Ammonium is the polyatomic ion from the molecule of ammonia. I mentioned hydrogen peroxide being in your medicine cabinet at home. Do not name that as dihydrogen dioxide. That would be marked incorrect. You need to remember that that is hydrogen peroxide. And of course, water, do not name as dihydrogen monoxide, but name that simply as water to receive your full credit. So I hope this helped you kind of clarify some issues with your ALEKS assignment, and thanks for watching. Have a good day.